Okay, hello everyone. Welcome to my review and my solutions to the VCAA VCE 2024 Northern Hemisphere Timetable Mathematical Methods Examination 2, which is the open book exam where you can bring in a CAS calculator and your bound reference. Of course, let's begin with multiple choice. A disclaimer, I did not really check my answers after my first attempt. So if you see any mistake, please put it in the comment section below. Okay, so multiple choice first. We have the period and the range of a trigonometric function, and the question is asking for them. And so you are supposed to know how to get the period from a rule of a trigonometric function, which is you take 2 pi and you divide it by coefficient of x. So in this case, we get 2 pi over 2 and we get pi, so that's the period. From this, you can eliminate 3 of the 5 options. I have circled pi here because that's the 2 answers that have the correct period. And then I look for the range, and then so here you're supposed to know that here's a dilation. So the graph will start with if you apply the transformation in the order Dr. T, if you do Dr. T, then the sine graph will have a minimum of negative square root of 3, and then you minus root 3, so you shift this down, so the minimum is negative 2 root 3, and then the Dr. T stuff, if you dilate, the maximum is positive root 3, and then you translate down by root 3, so you get maximum 0. And so option C is the correct answer. So this is all just transformation here. And then question 2 is a probability one. 2 events are independent, and it gives you the probability of A, the probability of A union B, and you need to find probability of D. So first we have the addition rule. Is it in the formula sheet? Yeah, it's right here. So anytime you see union, you can start to write this rule down. So A union B is A plus B minus A intersect B. And we know the union probability. We know the A probability. We're looking for probability of D. And so the only thing that we really don't know is probability of A intersect D. But you can see my highlighting here, and every one of you should have a highlighter in any exam setting. And you should be highlighting key points and keywords. So independent means the intersection is the probability of the intersection is A times B, the probability of A times the probability of B. So that's one of the properties of independent events, and you're supposed to know that, of course. And then so now we don't have something that we don't know, right? So A union B we know, A we know, B we're looking for, A we do know, and B we're looking for. So everything is basically set up. Sub the numbers in, substitute the numbers, and then at this point, you shouldn't be solving any equation by hand in exam 2. As soon as I write down an equation with one variable to look for, I am putting this in my CAS, and then I solve, and then I get 4 or 5. Question 3, logarithm. A, B, C are real numbers and they're positive. Look at my highlighting. I have highlighted positive. And the base is the same, so notice that having the same base means you can apply all sorts of logarithm rules. So you need to notice the base is the same. And so that's what I did. I applied some log rules. So combine the 2 logs on the left hand side of the equation. So A times B inside the log. And then 2 is really a power. So C to the power of 2. From this point onward, you can get rid of the log because log is a one-to-one function. So if they're equal, if 2 logs are equal and they have the same base, then the brackets are equal. So AB is equal to C squared. And then if you look at all the answers are really trying to rearrange the equation such that A is the subject. So I'm going to take what I got and rearrange to make A the subset, and the answer is D. Question 4. You have a straight line. It goes through the positive x-intercept of this curve here, of a cubic curve. And the straight line also goes through the point of inflection. And then it's asking for the gradient of the line. So I use CAS to find the x-intercept of the cubic here, which is 2, 0. I also used my CAS calculator to find the point of inflection, which is this point here. And from two points, you should be able to figure out the gradient of a straight line. It's rise over run. So the difference in y over the difference in x. And then to find the point of inflection, I think I double diffed the cubic. Let me double check. I think that's what I did. X cubed minus x squared minus 2x. Like this. Yeah, I think I double diffed it to find the point of inflection, which is somewhere in here. And then, oh, that's another one. Yeah, so double diff the cubic to find the x value of the point of inflection, substitute this back into the original function, and then you get the y value, and then rise over run to get the gradient. Okay, another probability one, a biased coin. So the probability of landing on a heads is 0.25. The coin is tossed 10 times, and the number of heads is recorded. So I've highlighted heads and heads, just in case they try to be tricky. And then sometimes when they try to be tricky, they'll give you the probability of heads, and then what they actually ask for is tails. And so you need to be careful if they're asking for the opposite of the information that's given to you. And then it says the probability that exactly X heads are recorded is, so this is a classic question where it's not really asking you to find something with your calculator, as in you couldn't really just plug stuff into a calculator and get the answer, because it's asking for the formula itself, right? And then so hopefully you realize this is a a binomial situation, because you have two outcomes really, and the probability from, you have two outcomes, you have a number of trials, you have 10 trials, and the probability of success and failure really in each trial is the same. It doesn't change. The probability does not change from one trial to the next. So it's a binomial situation, and hopefully you have the binomial distribution formula, probability formula in your head. If it's not in your head, hopefully it's in your notes somewhere, because this is open book, so you can always look it up. Okay, the next question, question 6, tangent graph, tangent AX, asymptote with equation x equals to the power of 6. And possible value of A is something. Well, you could do this properly, but it's not going to be pretty, because there are infinitely many asymptotes. There are infinitely many asymptotes in your tangent graph. And so if you try to, and you don't know which one this is referring to, you don't know if this is the first x-intercept after x equals 0, or second one or third one, and so on. And you don't really know what they're looking for. Like there can be many, as you can see here, possible value of A. So there can be many correct answers to this. Even just to achieve asymptote with equation x equals to the power of 6, you can have many A values that satisfy that requirement. So the trick here is not to do it properly. You need to do trial and error. To try the options, right? So you put 4 in, A equals to 4, put that in, and then you check if the function is undefined when x is power of 6. If x is undefined, if your function is undefined when x is power of 6, when A is 4, then that's your answer. Otherwise, you keep going. So this is what I mean. So This is what I mean. Tangent A times x. So I'm defining a function in terms of a and x. And if I try the first option first, which is 4, and the x is pi over 6, it is defined. This is defined. So this is not an asymptote. So when x is pi over 6, it is not an asymptote. So A is not my answer. And then I can copy that and then put 6 in. That's also defined. So that's not my answer. So option C is 9, and now that's undefined. So 9 is the answer. A equals to 9, which is option C. Now, it's a cost function with a lot of unknowns here, A and B again. It's got a period of pi over 3, a maximum value of 10, given that B is bigger than 0, minimum value of the function. So you can set up, basically, if there are two variables to solve, I shouldn't say variable, two unknowns. If there are two unknowns to solve, then you need two equations. That's something you should realize. So you need to set up two equations. One is the period. So 2 pi over b minus 1. So b minus 1 is the dilation factor. So 2 pi over the dilation factor b minus 1 is equal to pi over 3. That's the period. And then the maximum value. So if we also assume A is positive, if we assume A and B are both positive, for now, it doesn't really matter if you're wrong, because then we can realize we're wrong and then we try again. So if you realize, well, if you assume A to be positive and B to be positive, and we just add them, that should give you the maximum value, which is 10. Put them into a calculator and you get this answer, which is fine. It turns out we can be correct. A can be positive, it can be 3, and B is absolutely positive. It's going to be because the question says so, and it's 7. From there, you can find your minimum value, which is -3 plus 7. That's just dilation first and then translation. Okay, question B, discrete probability. Basically, here's the table, and it's a conditional probability question. It's given. I should have highlighted this. Let me actually do that, because it's always a good idea. Highlight the word given, is because it means it's a conditional probability. Given that a visitor previously visited the zoo, which means they've come here one or more times, what's the probability that they have previously visited more than once? So the condition is that they have previously visited the zoo, so 1 or 2 or 3 or 4 times, and then the probability that is asking for is more than once, so 2 or 3 or 4 times. So that's the setup, and then the intersection between the two events is just n bigger than or equal to 2 over probability n bigger than or equal to 1, and then here I didn't even bother writing it down. I just put this in the calculator. So on the numerator it's 0.25 plus 0.15 plus 0.05. On the denominator, it is 0.3 plus the rest. Okay, so quadratic here with the A in the middle. A is unknown, it's a real number. The set of values of A is such that f is bigger than 0 for all r value. So if f is bigger than 0 for all x real number, it means it has no x-intercept. I shouldn't say 0 x-intercept, that's kind of ambiguous. I mean no x-intercept is what I mean. I don't want to be ambiguous here. So the discriminant has, if I calculate the discriminant with the a value in it, the discriminant has to be less than 0, solve that on CAS, and then that's the answer. Yeah. Okay, and then you have a function f of x. It's a weird looking function. It's most likely a Hilbert function. And then find the value of k for which this is a probability density function. So to be a probability density function, the area between the graph and the x-axis needs to be 1. So we just need the area under the graph, between the graph and the x-axis. and it is a trapezium shape, so you need the area of trapezium. If you ever forget the area formula for a trapezium, it is also in the formula sheet, so you can come and grab it. And so plug all the numbers in with the k stuff. So this length is 2k. This length is going to be 4. And the height is going to be k, because that's the y value there, that's the height. Plug everything in, equals to 1, solve it, and get the answer. Okay, so here is the amount of hours of daylight per day. It is a cost function. T is the day of the year. T equals to 1 is 1st of January. During 1 year of 365 days, the number of days for which there are at least 11 hours of daylight. So this is my thought process. So the first thing is, of course, to define everything. 12 minus 3 cos, yep, 2 pi over 365 multiply x minus 175. There's no translation in, oh, actually there is, but it's in the front. Okay, so the first thing you should always do is to graph it, just to see what's to get an intuitive sense of what's happening. If I put that in, don't want that anymore, I just want h. Yeah. Oh, and it's not showing, which means I need to change my window of view. So it is 1 year of 365 days. So the t value goes up to. So I know that for 1, let me go to -1, and then this is just make it 370. So that's the t value, which in here is x. And then I need the maximum also. So you can see here very quickly, it's 12 plus 3. So 15, which means I'm going to make this something slightly bigger. And the minimum is -3 plus 12. So I'm going to make this something like this. Something like this. And now I can see that clearly. And so this is the graph for basically one cycle. The window of view has gone over a period, but that's intentional. And then I need 11 hours of daylight. So I need to draw 11. So this is y equals to 11. Yeah. And then it says number of days for which there are at least 11 hours of daylight. So it means I'm not looking for the middle part. At least 11. At least 11. So I should have highlighted this in the first attempt. It means more than 11 or equal to, more equal to. So here, the left hand side is what I need, and the right hand side is what I need. So you need to first of all get that point across, and with that point, we can then solve this for the intersection. Actually, that's a mistake. I need to put the domain in, and here we have it. So the intersections, there are 2 of them, and we've got 2 answers. And because I need more than 11 hours for this, for the first option, I'm rounding down, right? Because if I go to 104, I'm towards the right, which means I don't have 11 hours. I'm just below 11. So for the first intersection, I need to go to the left. I need to round to the left. So I'm going to 103, which is what I wrote on my paper. And the second answer, yeah, I wrote 247 here. That's because 246 point something, 246.5, 246.5 is here. I need to the right. I need to go to the right, not to the left. I need to round up on this one. So rounding up is 247. It's 247. And also, I'm looking at, the question says up to a year. doing 1 year of 365 days. So the last day also counts, right? Because the last day here, the amount of daylight hours is more than 11. This y value is more than 11. So the second portion is, the first portion is from 0 to 103, from 0 to 103, so it's just 103. But from 247 to 365, the amount of days is actually 365 minus 247 plus 1, because we're counting the last day and the first day, right? So on the 247th day and the 365th day, they're both correct. Like they both have more than 11 hours of daylight. So I need the plus 1, so it's 119. The count of days is 119. So 103 plus 119 is 222. So it's very easy to make a common mistake of 221 basically. They're being tricky here. The answer is 222. At least I think it's very easy to get the wrong answer, which is 221. Okay, and then we do Newton's method. Is the function a logarithm and a 4 minus x to the power 5 over 2, so not the prettiest function. But with the initial estimate of x0 equals to 0, x0 equal to 0, we need x3. Again, just in case you forget, the formula for Newton's method is on the formula sheet, so here it is. Usually I do this. You could have defined this on your calculator before you go into the exam. But to me, it's really quick enough, so it doesn't really bother me if you don't. So ln 2x minus 1 minus 4 minus x to the power of 5 over 2. And then we're going to diff this and then store it. And then store it. I'm doing this in 2 steps because sometimes for some things, it doesn't really work if you do the shortcut where you define and you differentiate in the same line. If you define this with the operation of differentiation in the same line, sometimes it doesn't work later. Sometimes. So I'm doing this in 2 steps to make sure it will definitely work. And then if you forget, you can just come here and then you type the formula of the Newton's method into your calculator, which goes something like this: x minus fx dfx. And so we can now start playing around. So if you sub 0 in, which is the first value, it's 0, x0 is the starting value, you get x1 equals to 2. So I'm going to write this down, x1 equals to 2, it's right here. And then you come up and you do the next one. So x2 is 1.5628, 1.5628. So that's x2, but we haven't got x3 yet. So come up and then do that again, and you get the final answer. And then you can look at the options. They're all rounding to 4 decimal places. So that's what you should do. You should round this to 4 decimal places. 4752. 4752. Option C. Okay, continuous function f and g, domain R, all real numbers. It is known that g is less than 0 for all x, and the differentiation of f is g, which means if you anti-diff g, you're going to get f. Given that f negative 1 is 2, f2 is negative 1, what's the area enclosed by the graph of y equals to g, the x-axis, and the line negative 1 and 2? So if we just do it, the area is integration from negative 1 to 2, g. Well, from this information here, we know that if you anti-diff g, you're going to get f, so f is here. And then we sub 2 in minus sub negative 1 in. Of course, we have this information also. F2 is negative 1, f negative 1, we also know that. And that will become negative 3. And it's a negative area because g is less than 0. G is a negative y value function, so we expect that. it just means the area is positive 3 square units. So yeah, we expect the negative answer coming out of the integration. It will just be a positive area that we have to answer. Next one. Y equals to x is over here. Cos x is over here, the curve here, and it's only part of the graphs. X is measured in radians, and then we have a pseudocode. It is to find where the two functions intersect, and then it goes like this: intersect x0, x1. So basically, those are two guesses of the x-intercept, and then x value is going to become x0. As long as the x0 is smaller than x1, which is the second input. So those are the inputs you put into the algorithm. First input, second input. So as long as the x value is less than the second input, which means when you put this in, when you execute this algorithm, you should put a smaller number here and a bigger number here. Yeah, so while that's true, while your x value is smaller than x1, they will look for the difference between the cos function and the straight line and the x function. If the y value difference is small, right? So if the y value difference is between 0.01 and negative 0.01, it means it's very close to 0. It just means it's very close to 0. If that's the case, we have found the answer. There's no difference between cos x and x, which means the y value is the same y value. They're intersecting. So if that's the case, we found the answer, so we return x value. X is the answer. If this is not satisfied, so the difference between cos x and x is too big, then we move the x value by 0.01 to the right. So we basically just keep guessing. And then we do this again. It's a while loop. So we repeat this. If we got to the end, right, if x value gets to x1 exactly, and we still haven't found something that's close enough, then it will just tell you there's no intersection that's been found. Okay, and then the function says 0.6 to 0.8 is the input, right? So we are running this code, and 0.6 is what we're putting here, and 0.8 is what we're putting here. What will the function return? Well, actually, my first reaction was I'm gonna do a desk check, and then I'm gonna put x equals 0.6 because that's what the first thing says. X is gonna be x0, so 0.6 to start with, and then do a desk check. So I'm gonna find cos x minus x, and so on and so forth. And then I thought, okay, next step is plus 0.01. So x value is going to be 0.61. This is going to take many steps. This is going to take many steps before it gets to 0.8. If I'm not lucky, this may be the case. So I thought, okay, I'm not going to desk check. I don't have enough space to desk check that many lines anyway. It's going to take many lines before I can get to 0.8. And then I thought, okay, I'm gonna write this code on my CAS using Python, which I did. I actually did that here. So you can kind of pause the video and look at the code. And then I ran it, and then I found the answer. Actually, found the answer with the code that I wrote. But then I realized that is stupid. You don't really need to writing Python code in your exam during the 2 hours you're given will be very difficult. It will be wasting a lot of time. You're going to take a lot of time to write your code in Python in the exam. So that is not exactly the smartest, wisest move to make. And then so I crossed this out. I regretted my decision, and I crossed this out. And I realized you could just use CAS to check very quickly, like this. A and B are basically not it, right? Because if you look, if you can understand the pseudocode, whatever output you have for the x value, it is going to be between x0 and x1. So whatever x value the program outputs, it has to be between 0.6 and 0.8. It could be inclusive. It has to be between 0.6 and 0.8 inclusive. So A and B, they're definitely not it. So you can look at them. C, D, E is your question. And then so you can try this, right? you can see that x value increases every time. So x value increases every time. So when you run the program, it's going to get to 0.73 first, right? So the computer is going to get to x equals to 0.73 first, which means we can check this. We can, what did I do? I need to go here. So which means I can define the function that the pseudocode is checking, which is cos x minus x. Also, at this point, I'm going to check my radian, make sure it's correct. And then, so if the pseudocode gets to 0.73 first, I'm going to look at this and go, okay, the pseudocode is going to go 0.73, and it's going to check the y value, 0.015. Pseudocode is going to know that this condition is not satisfied, right? So cos x minus x is not between 0.01 and negative 0.01. It's bigger. It's bigger than 0.01. Cos x minus x is bigger than 0.01. You can see in the calculator. So it is not going to return 0.73. It is going to come down here, add 0.01 to it, and now it's going to check 0.74, which is what I'm going to do manually. And here you can see negative 0.001. This is now between negative 0.01 and 0.01 because it's got 0.015, 2 zeros after decimal place versus 1 zero after decimal point. So the calculator is going to recognize, the computer is going to recognize when x is 0.74, this condition is met, this condition is satisfied, so it will return x and it will terminate, which means 0.74 is what we're going to get, what the computer will spit out, 0.74. So 0.74 is the answer. If you understand the pseudocode, you could do this very quickly by manually checking on your CAS with some calculation. You don't need to write a Python code or a desk check. None of that. It will just be a big waste of time. Yeah, so let me get rid of this actually. Get rid of that. Next one. Okay, so we have a company. Production cost per item, our highlighted cost per item is this much. It's quadratic. Well, not exactly. There is a 1,250 over n over here, where n is positive integer. So z is integer. So you're supposed to know what z means. That means integer and it's positive. And n is the number of items produced. The minimum cost per item is closest to. So actually, the first thing I did was actually, yeah, the first thing I did was I graphed this function to make sure it is the absolute minimum is the same as the local minimum. We're looking for the absolute minimum, and so we need to determine if that's also the local minimum to give us some idea. And once I have determined that is the case, the absolute minimum is the local minimum, I just differentiated the cost function and I make it 0 and I solve for it. And once I get the n answer for n, I still need to substitute that back into the c function and I get the answer. So you can't just find n, you need to sub n back in to find the actual cost. Okay, and then we have two continuous function and their derivative f and g, x0, x2. And then we have differentiate GOF. This is a function inside a function. So this is your chain rule happening here. Which means we are substituting f function into g function. So what we do is we diff f, we multiply diff g, and then we sub f back in. I believe the chain rule is also in your formula sheet. So if you ever forget, you can come back to this. And then because I'm looking for x equals to 0, I'm going to sub x equals to 0 in, but then f dash 0 is given to me, it's -1. f0 is also given to me, which is 2. But then f dash 2 is also given to me, which is 3. So -3 is the answer. Okay, probability. So a given b is 1, c given b is c. which of the following statements about A, B, C are true? Must be true. Must be true. Okay. First reaction I had when I was reading the question was this: C given D equals to C. It means C and B are independent. That's the first thing it means. If the probability of C is the same as the probability of C given that D has happened, it just means C does not care, does not depend on B, and vice versa. So C and B are independent. That's the first thing I wrote down. And then the second thing I wrote down is, and from the first statement, I see one. One is a special number. One is a special number in probability. It's the theoretical maximum probability of any event, any sample space, any experiment. So one is a very special number. So once I see one, an alarm bell is ringing in my head. What does this mean? A, if B has happened already, the probability of A happening is for sure. Right? So let me repeat. It means once and after B has happened, the probability of A happening is 100%. It is certainly going to happen. Event A is certainly going to happen, completely certainly going to happen after B has happened. So which way is it? Right? Is it this sort of thing going on? It's B inside A, or is A inside B? Right? Let's have a look at this. So B condition is B. So B happens first, and once B has happened, in this scenario, A must happen, right? Because B, if B is inside A and B has happened, then A has definitely happened. Here, not the case, right? In this scenario, if B has happened, you don't have to be inside A. So the probability of A happening is not 1. It's not certainly 1. So I've crossed this out. So from these two pieces of information, I can make two conclusions. B and C are independent, and also the relationship between A and B is this sort of a Venn diagram, if you like. This is kind of a part of a Venn diagram. Okay, so probability of A equals to 1 can be the case, but it doesn't have to be the case, right? It's not a must be true statement. Yes, the information gives us two pieces of information only. From these two pieces of information, it is not certain that probability of A is 1. It can be, but it doesn't have to be. Also, C is a subset of B. That is just not going to be the case because C and B are independent. Probability of A is not 1. The argument is the same as A. It is possible that the probability of A is not 1. But then again, it doesn't have to be. We can't conclude this from the two pieces of information given to us. And then I'm going to go to E now. I'm going to leave D later. Option E, B and C are not independent. Well, that's clearly the opposite of what we concluded. So E is gone. And so D now. D and C are independent. That's good. D and C are definitely independent. And the subset of A, which is what I drew here. D is a subset of A. Those two things, you can conclude those two things without even looking at the options, is what I'm saying. As soon as I see those two statements, I can make some sort of a conclusion from them without looking at the options, and then look at the options, and then they're exactly the same as what I did. So option B is the answer. B is a subset of A, which is this diagram here, and B and C are independent. Next one. A cost function with A inside, A is bigger than 0, there's a unique solution to fx equals to 1 and a unique solution to fx equals to -1. The minimum possible value of A, again, you could do this properly. You could do this properly, but why would you? It would take a long time to do this properly. So all I did was try an error. So a very similar idea. You define a function with two variables, two inputs, A and X, and then you got cos A times X plus pi over 6. And then what? There's a unique solution to fx equals to 1, right? So Basically you want this. Yeah, you want this. So you want algebra, system of equation. And so you want, there's one unique solution to fx equals to 1. So 1 is equal to f, and then you put the first option in. So a is 1 over 12, 1 over 12, x is still x. And then the other equation is negative 1. And it says there's a unique solution to that. And again, I'm trying option A, so 1 over 12 x. And that, well, and it says false. I'm not even putting in the domain here. If I type everything correctly, cos ax part of 6. Yeah. Yeah. And I'm not even putting in the domain here, and it says false. So that didn't work. And then so you keep trying. 5 and 5, that's also false. So option B is gone. So option C, 5 over 6. So 5 over 6 is what we want. Over 6, that's also false. There's no solution. And then 11 over 12. So the next option is option D, 11 over 12. So we are going to do that. 11 over 12, 11 over 12. That didn't work either. What did I do before? Did I do something else before? No, there is no y value. That's why I didn't type it. I didn't type it correctly. Yeah, that's what I need. Type it correctly. It's a unique solution, or is it that I just did this? Oh yeah. I remember now. I just solved them one by one, actually. I didn't really solve the simultaneous equation. So try the first option again with the domain. So I'm trying this equation, fx equals to 1. And option A, 1 over 12 is the A value. And then I have the domain. I've done this correct. Yep, I've done this correctly. And that is false. And so I try something else. I'm only trying fx equals to 1 at the moment. And so the next one is 5 over 12. So I'm going to try that. That's also false. And then 5 over 6. That's also false. And then 11 over 12. 11 over 12. That's one answer. So there is a unique solution. There is a unique solution to fx equals to 1. When a is 11 over 12. But there should be another one when fx equals to negative 1. So here is what I try. And there is, of course, a unique solution. And then the next part is I'm still going to try option E, 17 over 12. So 17 over 12. There is a unique solution. But if I do this, if I do negative 1, so if I do the other equation, which is fx equals to negative 1, there is a two solutions. There's more than one answer, so it is not a unique solution. But if you do trial and error, you are going to get 11 over 12 to be your A value. Yeah, my mistake. There's the question does it's not the same solution to the two equations. This is not a simultaneous equation situation because the unique solution to this equation is different to the unique solution to the other equation, and it's a cosine, of course. So we expect that the different y values. Okay, almost there. So next one, f is a continuous and differentiable equation. Part of the graph is shown here, and then -1, f -1 is a stationary point, and when x equals to 3, it's also a stationary point. It's given to you. This question, I did think about this for a little bit, but let me actually continue with the question. the solution to the inequality x squared minus x minus 2 f dash times f dash. So x squared minus x minus 2 all in brackets times f dash is bigger than 0 is something. What solution for x? So I actually tried to find the equation for f, and that was a failure. That did not go well. We don't need any of this. Yeah, so my first instinct was to find the actual rule for the function f. That just didn't work because there isn't enough information here. So you shouldn't attempt it. Well, actually, when you have time, I encourage you to do so. And if you do, please tell me what went wrong, why this is not going to be a fruitful exercise. Please leave that in the comment section. It will be interesting to have a discussion. You could say there's not enough information here, but there's actually something deeper going on here that prevents us from finding one possible rule for the graph of f, or rather, there's something deeper going on here. That means even if we find one possible rule for the function f, it doesn't really help us. So if you do attempt this method, please leave it in the comment section below and tell me why it wouldn't work. Or if you think it does work, also let me know. But then I gave up pretty quickly after trying to find a rule for f. And then I thought, let me just not do this analytically. Let me move away from actual proper algebra and proper on-paper proof. I'm just gonna do it visually, do it graphically. So here's my attempt. Because I'm looking for f dash in my inequality, so I'm gonna draw f dash. And here it is. Right? It's f dash. This is f dash. It should have a x-intercept when x equals to -1, which is here. It should also have an x-intercept when x is 3, which is here, because the f dash is 0. The y value of f dash is 0 when x equals to 3. And then let me go back to -1. To the left, it's a negative f dash. So I'm looking at negative f dash here. And then from -1 to the right, I'm looking at positive gradient. So f dash is positive, which means it's going like this. It's positive. And then to the right of x equals to 3, it's a negative gradient on f. So negative f dash graph. So here's a kind of like a parabola f dash. And then I decided to graph x squared minus x minus 2. And it just happens, and I did this on CAS, by the way, I'm not graphing x squared minus x minus 2 by hand. It happens that the x-intercept of x squared minus x minus 2 is -1 and 2. That's the x-intercept. So I graph them. It's an ugly graph, but you get the idea. And then I multiply them bigger than 0. Well, to the left of -1, there's two y values actually, but we are multiplying two functions. One function is x squared minus x minus 2. The other one is f dash. So we are multiplying two functions. We're multiplying the two y values. So to the left of x equals to -1, one y value is positive, one y value is negative. Positive times negative, always negative. So that's definitely what I don't want. I definitely do not want anything x value less than -1, because it's going to be positive times negative, which is negative. X equals to -1, I also do not want that, because it's 0 times 0. It's not bigger than 0. Over here, to the right of x equals to -1, I also do not want it, because it's again a positive x value times a negative a positive y value times a negative y value, which is positive times negative. The whole product is negative. So I don't want any of that. And so I can keep scanning to the right. So positive, negative. Up to this point, I still have positive, negative. And then here, so to the left of x equals to 2, I still have negative times positive. But then when x is negative, when x is 2, I have 0. So that I don't want either. 0 times anything is 0. And then to the right, though, if I go to the right of x equals to 2, I have positive times positive, which is positive. So that's what I do want now. I do want x bigger than 2, because y value is positive times positive. all the way to here, still positive times positive, 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 until x is 3. Because when x is 3, it's 0. And then when x is bigger than 3, so to the right, I have negative times positive, which I don't want. Conclusion. I want everything between x equals to 2 and x equals to 3. Option C. Okay, so this is a question you have to solve graphically, visually, and you can't use CAS. CAS doesn't really help. It just, well, I mean, you draw the graph using CAS. You can draw x squared minus x minus 2 using CAS. That helps. Otherwise, it's more of a thinking question than a CAS question. Okay. Function x squared bracket 1 minus x squared. It's a quartic. Another function g, which is a translation of f. Find all the real values of a such that g0 is the absolute maximum of g. Also, f has no restriction on the domain. G has a restriction on the domain. This is a fire question. Fire means it's quite hard. And in this question, the CAS is very important. Okay, here we go. Yeah. This is a fire question. Fire means, when I say fire question, it means it took me a long time. It took me a lot of thinking, a lot of slow thinking, and a lot of time to get to an answer for which I'm satisfied. Okay, so let's define f to begin with. X squared 1 minus x squared, and there's no domain restriction. And then I'm gonna do this. I hate slider. If you don't really know my style, I hate slider on the CAS. I almost never use it. So what I do is I always define whatever is to be the slider, so a, in my function as a input. So a is the input to the function, and then I can do x plus a like this. So that's my function g. Okay, let me start a fresh graph. Here's what I'm gonna do. I am going to put, let's begin with a not there, so 0 and x. So let's just for f is what I'm saying, and a is I'm doing a equals to 0. But here's the key thing to do, and I only realized that after some time. You have to draw the function g with the domain. So that's it. Also, if I haven't told you this before, when you define a function, you should never have the domain in the definition. So not this. You should never do this, please. When you define a function, you do not put the domain in. The reason is this. If you define the domain in the definition of the function, it makes the job much harder for the CAS. The computational load that the CAS algorithms have to go through if the definition of the function includes the domain becomes a lot heavier than if you only put the domain in when you execute the command. So only put the domain in when you are doing a command or a functionality of the CAS. Do not put domain in a definition of a function. All right, so here we go. Can't really see that clearly, so let's improve on that. And I know my domain for sure, so let's do that. Okay, here we go. When a is 0, clearly g0 is not the absolute maximum. It's just not there. Okay, here's what we're gonna do. Sorry, I forgot. When I was exploring the question, I actually sketched the graph of f first. This is y equals to f. And here are the turning points. 0 is also a turning point. And those are the coordinates. Those are going to be important because when we talk about absolute maximum, we almost always have to consider the turning point, the local maximum. So you should know where the local maximums are, even though you are looking for absolute maximums, which can be not the same. So yeah, draw the graph of f first is what I should have done. Should have told you, but you use your CAS to do this. Okay, and then so we kind of know what this what this coordinate is, but we do know what the coordinates of that turning point are. The coordinates are those ones. Okay, here's what we're going to do. We are now going to consider just positive a, because a is not 0 for sure. Otherwise, G0 is not the absolute maximum. We want G0 to be absolute maximum, which means when x equals to 0, we want maximum. It's not. A is not 0. We know that. Now we check what happens if a is positive. Right? If a is positive. Also, it would be nice if you knew the decimal for the x value, the decimal value for the x value of the turning point. Root 2 on 2. So let's do that. Root 2 on 2. That's roughly 0.7071. Okay, so let's write that down. That would be nice to have. 0.7071. That would be nice to have when we check our stuff, our a value. Okay, so here we go. So if this is 0.7071, I know what roughly how big I can pick my a value to be, right? So over here, if this is 0.7071, if I pick my a value to be 0.1, I'm not picking a value that's too big. Right? I'm confident that it's not too big of a value. And I can see here, right, that G0 is still not a maximum. And G0 is still not a maximum. And I think I kind of drew this graph here. I drew all of it. I didn't really just draw the domain restriction. And then, yeah. Then I basically kept going, right? So I basically kept going. That's still not maximum. That's the maximum, but I realized something. This is 0.8 is 0.3, but I realized something. G0 is getting close to being the absolute maximum now. Right? When a is 0.4, it's getting close. It's getting close. Right? So here, and now it is definitely the absolute maximum. Right? So let me backtrack. When it's 0.4, G0 is getting close to being the absolute maximum. And then when I go to 0.5, a is 0.5, G0 looks like the absolute maximum. When did it take over? When did G bracket 0 take over as the absolute maximum? Well, when these two y values are the same, right? There should be a point where there should be an a value. There should be an a value where these two y values are the same, right? In which case, if the two y values are the same, and G0 is the absolute maximum, because that's also the absolute maximum, you can have 2 points being the same absolute maximum. And then from that point onward, if we increase a even more, it will keep being the absolute max. So that's what we need to find. We need to find the a value for which the y values are the same. And is it half exactly? Did I write half exactly? Oh, I said half exactly. Well, at this point, we don't know if it's half exactly. So this is what I did. To find the a value for which the two y values are the same, I'm coming here. So G, A, I don't know. I'm looking for A. That I want to be that. So when x is 0 and x is 1, I want the G value to be the same. And it turns out A is half. So it turns out A is half. When A is half, the y values are exactly the same. So it is absolute. So this one G0 is absolute maximum. And I didn't write this down on my paper. A is half, but what I actually did behind the scene is I actually confirmed. I pretended I did not know the answer, and I didn't know the answer really when I was first doing this. They know the answer, and all I was trying to do is ask the calculator what a value will give me the same y value when x is 0 and x is 1 and it's half. All right, so that's good. That confirms it, and I can keep increasing it, still absolute maximum. Okay, G0 is still absolute maximum. Now, when it's 0.7, it looks like it's still absolute maximum, so that's good. But, like I said, you've got this point here. We are getting close to this point here now. So when it's x minus a and a is positive, we're shifting the whole graph to the right. If a is positive, the graph of f is shifted to the right. So this local maximum is getting close to the y-axis now, which means root 2 on 2. So let's actually do that. So if I do this, exactly, root 2 on 2, the local maximum is coming up here, which is the which makes P0 the absolute maximum. And I can keep going, right? Let me keep trying to increase a value 0.8. And now see, that is not the absolute maximum anymore. That's not the absolute maximum anymore because the local maximum is over here now. And you can see this if you know what the translation is doing. It is, if a is positive, it's shifted to the right. So once you go past this point, like once the local maximum here comes to the y-axis, and you keep moving to the right, you keep this moving to the right, you're looking at this part of the graph here. And so G1, this part here, the left is always smaller, the right is always bigger. It doesn't matter how far right you go. You can go very far right, and you're here. The left is going to be smaller, the right is going to be bigger. So G0 will never be the absolute maximum again. So you can keep increasing this, and it can be a very big number even. It's just going to get out of the window. If I do a 5, it's going to be out of the window. So somewhere here. It's hard to, yeah, it increases a lot. Let me actually not do that. So carefully. No, I'll give up. It would just be very far down. Hopefully I can see it. Is it happening? Yeah, right here. It's very far down. And you can see it doesn't matter how far to the right you go from now onward. The left is smaller, the right hand side is going to be bigger because that's what the graph is, and you're shifting the whole f to the right. Okay, so let's go back to what I had before. Okay, so that's the positive side. So from positive, I know it's half. So A starts at half and it can be bigger. A can be half, and then the largest A value I can get is root 2 on 2. From that point onward, I'm looking at this portion, look at my cursor here, I'm looking at this portion of the f function, and that's not going to give me what I want. Okay, so E and E are my answers. E and E are my answers. Not A, not B, not C. Because I have this part here and this part here. And those two, the interval from half to root 2 on 2 is what I want. Interval from half to root 2 on 2. Okay, the other question now is, it's symmetrical, right? So if A is negative, would that be symmetrical A value? Well, let's find out. So again, start with A equals to 0. Just make sure everything is working. Yep, it's working. All right, so now I'm going to do negative 0.1. Okay, P0 is not the absolute max. 2, still no. Keep going. 3, still no. 4, still no. 5, still not. The G0 is still not absolute max. 6, getting close to it. 7. Ooh, looks like maximum max now. Absolute max now. So the question is, what do you think is happening here? Right? So is it actually negative 0.7? Is the number we're looking for? Is it actually, are we actually looking for the number negative 0.7? Well, you need to think about this. You need to think about what this is actually doing. it's shifting the graph to the left, shifting the whole graph of f to the left. So you start here to the left. Well, so basically, this local maximum will never happen. We're doing negative a value now, right? So if it's negative a value, this local max will go to the left. It will never be in our window domain, 0, 1 domain. So it's this maximum, this local max that's doing the trick. And so if you visualize shifting this graph to the left, and you're at G0, those points here are not going to be your local max until you hit this point, right? So when this local maximum comes to the y-axis, when this local maximum comes to the y-axis, you get G0 absolute max. So the negative a value starts here. The negative a value starts at negative root 2 on 2. Negative root 2 on 2. And then, so the negative a value starts at negative root 2 on 2. So negative root 2 on 2, like this. And then you can make it even more negative, right? So negative 0.8 is also absolute max. Negative 0.9, also absolute max. Negative 1, also absolute max. And you can see that makes sense because if you move this whole thing to the left, after the local maximum hits the y-axis, you keep moving to the left. In the window that is 0 to 1, x is 0 to 1, you're looking at this part here, right? So for your domain 0, 1, you're looking for this part here, where left is always bigger, the right is always smaller, and you can move to the left however far you want. You can move to very far left, and then you also you're always looking at the shape like this. The left end point is bigger, the right end point is smaller, the y value is smaller. So actually, when you go negative, you can go negative infinite. You can go to negative infinity. So that's the answer here. So from the negative side, we start from negative root 2 on 2, and it's inclusive, and we go to negative infinite. So the answer is E. The answer is E. This explanation that I'm giving you and the thinking behind it and all the graphs that I drew, hopefully they make sense. But even for me, they only made sense after quite a few attempts and some time of thinking and playing around with graphs and numbers and things. So yeah, this is a very difficult question. Hopefully what I said makes sense. Okay, so that's the end of this video. For the rest of the exam, please see the other videos. Thank you.